to study something. I'm very grateful to share one of our recent work. In this talk, I'm going to introduce a specific paper which is published in Science last year. This work is done with Dr. Guo Gaozhang and Ms. Shan Zhi, and advised by Professor Zhigang Suo. So elastomers and gels are what we studied. These type of materials are widely used in diverse applications such as tissue regeneration, bioadhesives, bioprints, wearable electronics, ionotronics, and soft robots. I have listed some papers, very important papers in these applications here. And as soon as you open these papers, you will see elastomers and gels. So what is the reason? The reason why these type of materials are widely used is that the properties of these materials are very similar to the living tissue. So as soon as you want to mimic the biosystem or get some inspiration from the biosystem, or if you want to integrate with the biosystem, you probably want to use elastomers and gels. So let's take a look. What are they? They are cross-linked rubbery polymers. That means the glass transition temperature is lower than room temperature, so the polymers behave like a fluid. That is the origin of the softness of these materials. And if you take a look at this schematic, you can see how the elastomers are made of. There are polymer chains. Again, the polymer chains are vibrating by its thermal motion, but they cannot explore the entire volume because they are cross-linked and connected into a network. So you can define a chain by two crosslinks like this. Then this chain cannot explore the entire volume. It only explores the limited area defined by the two crosslinks. Okay. If you put these elastomers in the solvent of the polymer, then the solvent molecule will start to be mixed with the polymers like this. Solvent molecules, polymers are mixed. We call this as gel. If the solvent is water, we call it as hydrogel. Essentially, the structure of the polymer is very similar. Polymers, like a fluid, are cross-linked and then connected into a network, so they cannot change the topology because of the crosslinks. So these systems are very similar, and we can apply the similar mechanisms for these two types of materials. We can control the stiffness of the elastomers and gels very easily by controlling the density of crosslinks. If you put lots of crosslinks, then the chain becomes shorter because the long polymer chains may have many cross-linking points, and then the chain becomes shorter. When chains become shorter, the material becomes stiffer. If you put less crosslinks, then chain becomes longer and becomes softer. That's how you typically control the stiffness of these type of materials. So stiffness, there's no issue, very easy to control. How about toughness? People use toughness in various ways in common communication. However, in the fracture mechanics, there is a very clear definition on toughness. The definition of the toughness is following: the energy you release as a result of the crack propagation. So let's say we have a sample, and let's take a look at the crack. The reason why we take a look at crack is that all the fracture starts from a crack. So let's take a crack and let's start to gradually stretch the sample. As you stretch the sample, you store the energy on the sample. Let's say the crack didn't propagate yet. You stretch more, store the energy more, and then suddenly the crack will propagate. When the crack propagates, you release some energy stored at that area, and then crack will propagate. then you can measure the energy you release as a result of the crack propagation. That is the definition of the toughness. So let's say we have a tough materials. That means you can store more energy, and when the crack propagates, you release more energy. Tough materials behave like this. How about brittle materials? You cannot store a lot of energy because the crack will propagate very soon. So in that way, we can also consider the toughness of the polymer networks. So this is the this model is introduced in 1967, which still works very well. So at the crack tip, there will be a polymer chain. And then as we stretch the sample, then this polymer chain will be stretched into a line. And then if we stretch more, then we will stretch the individual carbon-carbon covalent bond along the polymer chain. And you will simultaneously extend the individual covalent bonds all together. And once you break one, then it snaps and releases the energy stored along the chain. Therefore, if your chain is longer, you can store more energy, which makes your materials tough. If your chain is short, you cannot store enough energy at the chain, and after the crack propagates, you release less energy. That means your material is brittle. Therefore, the crosslinker density governs both stiffness and toughness. Let's say we put dense crosslinks, then chains become shorter, the material is stiff, but at the same time, materials cannot be tough. Again, the amount of energy you store in a chain is less, which is linearly proportional to the length of the chain. Okay, let's make tough materials. Then we can just put less crosslinkers, making chains longer and store more energy. Then you can make the materials tough. But at the same time, you cannot increase the stiffness. Then the material becomes extremely soft. So in our lab, I tried to make it tough, the hydrogel. So I put very limited amount of crosslinkers in the precursor and made the hydrogel and put in water. And it was swollen excessively like a runny nose. I even could not handle the material. So there is a stiffness-toughness conflict. You cannot increase both at the same time. However, people have developed many ways to tackle this problem. The one example is fillers. So you can put carbon nanoparticles into natural rubber to enhance the stiffness and toughness, or you can put silicon nanoparticle into silicon rubber. Then you can increase the stiffness and toughness at the same time. However, there is a drawback, shortcoming of this strategy, that is elasticity. So let's take a look at the mechanism of these fillers. Around the filler, there will be polymer networks, matrix, and there is adhesion between the particle and the polymer. When you stretch the material, because of this difference between the difference of the stiffness between the nanoparticle and the polymer, there will be stress concentration around the nanoparticle. You concentrate the tension around the nanoparticle, then you start to break this adhesion. That dissipates the energy additional to the polymer. So you release more energy when you stretch or the crack propagates. However, this process is absolutely irreversible process. That means you will see huge hysteresis under stress loading and unloading curve. And the materials cannot heal this damage as soon as possible because the adhesion requires some energy and time to recover to the original state. Therefore, it suffers fatigue damage and suffers fatigue resistance. So the fatigue resistance is relatively low compared to others. There is another way to increase the stiffness and toughness altogether. That is interpenetrating networks that has been extensively studied in recent decades. The principle is very similar to the fillers, though. You apply the secondary and third networks in addition to the major primary network, so that these additional networks break instead of the primary chain and dissipate additional energy as a result of the stretching. However, it is also dissipating mechanism and results huge amount of hysteresis under loading and unloading curve. Again, it suffers fatigue damage, and fatigue resistance is relatively low. The reason why these materials are inelastic is because this toughening mechanism and stiffening mechanism rely on this inelastic dissipating mechanisms. So before this paper, our paper, people have believed that if you want to increase the toughness, you need to increase the area between the loading and unloading curve so that you increase the amount of hysteresis. That was a kind of material design principle. If you need tough materials, increase the hysteresis. But obviously, these kind of materials are only tough at the monotonic loading. For the second loading, it becomes brittle. It becomes weaker. You degrade the properties under cyclic loading. So I didn't like it. And I asked that myself, that how can we make elastic but stiff and tough materials? That was the question we had. So we had hypothesis like this. What if we use entanglements more actively to tackle this conflict? So this is our hypothesis. What if we have an extremely long chain like this, extremely long, but densely entangled? Then the stiffness will be governed or will be maintained by these dense entanglements, but the toughness will be maintained by long chain, because we can store extensive energy along the extremely long chain. That was what we had as a hypothesis. Then we made a sample using molar system, polyacrylamide hydrogel. Typically, these type of hydrogels were synthesized with lots of water because it is hydrogel. People want to make this material as a hydrogel that has large amount of water. So in the precursor, there were also a large amount of solvent like this. After you polymerize this mono and crosslinker, then polymers barely entangle each other because of the low concentration of the polymer. However, in our case, we needed dense entanglements. So we put less amount of solvent so that this polymer and monomers are crowded. After polymerization, obviously this polymer chain inevitably entangle each other. So let's take a look at the photo of these two materials. We put the same amount of crosslinkers, which means we put one crosslinker per 30,000 monomers in both cases, but only difference was the amount of solvent in the precursor. At the left-hand side, we put 2 water molecules per monomer, and for the right-hand side, we put 25 water molecules per monomer, and polymerized and put into the water to swell to equilibrium. If there is no effect of the water molecule, then they must have the same equilibrium state. So it should be the same after they reach to equilibrium, but the result was obviously not. For the less solvent one, it was very stiff, even though it is in the equilibrium state. At the right hand side, we put more water molecule for this sample, and after we swell to equilibrium, this material was very soft and very weak. Let's take a look at the VUBI. So this is regular hydrogel. That means we put enough water molecule at the precursor. That means entanglement is limited. Sparse cross-linkers and sparse entanglements. It is weak. It spreads a lot. However, if you put less water in the precursor, the polymers entangle a lot and stiffness is maintained by the entanglement. So it is very stiff compared to the regular hydrogel. Again, this material is fully swollen in water. So we also measure the quantity. So y-axis here is the final polymer content at the equilibrium state. And there is two parameters. One is W and C. W is the molar ratio of the solvent to the monomer at the precursor. So 2 means there are 2 water molecule per monomer at the precursor. So it is very limited amount of solvent. 25 means there are plenty of water molecules in the precursor. As you can see here, 25. Obviously, this final polymer content is a function of cross-linker density. Cross-linker fraction is molar ratio of the cross-linker to the monomer. 10 to minus 3 means there is only one cross-linker per 1,000 monomers. So because the entanglement density is very negligible, this elastic property is only a function of cross-linker density. However, if you decrease the W value, that means entanglements densely the polymers densely entangle, then there is a regime that is not a function of cross-linker anymore. That means at this regime, the elastic property is a function of density of entanglements. And this plateau value is a function of W, as you can see here, then is another evidence that at this regime, the elastic property is governed by the density of entanglements. The stiffness has the same trend. There is a plateau where the elastic property is not a function of cross-linker, rather is a function of the density of entanglements. So we saw that at these recipes, at this combination of parameters, we make dense entanglements and sparse crossing. As we discussed before, there is no filler. There is no secondary network that dissipates additionally. Therefore, this material is extremely elastic. The hysteresis between loading and unloading curve is negligible. You cannot see it was less than 1%. And also there is no dependence on rate. So we changed the loading rate from 0.8 per second to 0.008 per second. We couldn't see any difference. That means this material is at very, very elastic materials. Viscoelasticity, the dissipation under deformation is very limited. Therefore, we just demonstrate this elasticity. We just plug the sample. For our sample, it vibrates very long time. But for the double neutral hydrogel, which is commonly known as tough hydrogel, it damps out immediately because it dissipates energy and damp out the vibration. And also we drop the ball on the sample. Our sample bounces the ball much more than double neutral hydrogel because it absorbs huge amount of energy right away. So, and we measured the toughness. We changed again the value of W and value of C and measured the toughness and plotted in this plane. As you can see here, there is very limited dependence on W. W refers to the density of entanglements. So we can see that the toughness does not change according to the density of entanglements. Rather, it was only a function of cross-linker density. That means the toughness comes from only the length of the polymer chain. That is the same as what we expected at the beginning, as at the hypothesis. And we see that the entanglements do not embrittle the materials, unlike cross-linkers. In the case of the cross-linkers, if you put more cross-linker, you can stiffen the materials. This is the same as entanglements, but crosslinkers embrittle the materials because the chain becomes shorter, the energy you store per chain is less and becomes brittle, but entanglements do not. It only stiff the materials and do not embrittle hydrogel. That is what we discovered in this paper. So in this case, we can increase the toughness without using huge hysteresis between the loading and unloading curve. So we plotted the stiffness and toughness at the same time in a plane. So in the regular hydrogel, you can see clear conflict: stiffer, brittle, more brittle, softer, tougher. But in the case of the highly entangled hydrogel, you can both get toughness and stiffness at the same time. And we also measure the strength. In the case of the regular hydrogel, it doesn't matter how much you put the crosslinker. Those are very weak. Compared to these regular hydrogel, highly entangled hydrogel is much stronger than regular hydrogel. Stiffness can be similar by putting more crosslinker, but the regular hydrogel becomes brittle and the strength is limited like this. Soft one is too soft. It's more stretchable, but cannot lift a mass like this, but highly entangled hydrogel can be used as a load-bearing materials because it is stronger. So we explain this behavior with the deconcentration of the tension. So if the polymers are highly entangled and if the polymer is very long, you can distribute the tension to many chains. That makes the polymers stronger. We also measure the fatigue resistance. So we made a cut and put into water and applied the cyclic loading and measured the crack propagation per cycle. So we measured the energy release rate where there is no crack propagation at all. That was 200, which is several times higher than regular hydrogels. We also measured the friction. Compared to the Teflon, the highly entangled hydrogel had about 6 times lower friction coefficient. So if you just grab this sample, it's very hard to grab the sample because it is too slippery. The reason why it has very low friction coefficient is because there is very long chain on the surface. This long hydrophilic chain stabilizes a thick layer of the water that makes the friction very low. We also measure the wear resistance of the material. Because this hydrogel has very high toughness and stiffness and low friction at the same time, and fatigue resistance is also high, so the wear rate was even better than most of the regular rubbers, even though it has 80% of water in the polymer network. It just it highlights the mechanical durability of this type of materials. Because the concept can be also used in elastomer, we also made elastomer version. So we used polyethyl acrylate. You can see the plateau as well. You can see the relevant the relation between the crosslinker and toughness like this. That means the toughness comes from the length of the polymer, and the hysteresis is very limited, which means we get elasticity as well. These are all the same behavior with the hydrogel, and the strength is about 10 times higher than typical polyethyl acrylate. We also measure the fatigue resistance, fatigue threshold, which is few times higher than other type of elastomers that have similar stiffness. So it has clear benefits on durability of the polymers. Let me conclude. So we have studied how entanglements affect fracture. We see that entanglements stiffen elastomers and gels, but do not embrittle them. That made us to make the material stiffen both at the same time without using in elasticity. So material is elastic, but we can get stiff and tough materials at the same time. I thank Dr. Guo Zhang, Ms. Mei Suanzhi, and Professor Zhigang Suo for intensive collaboration and discussion, and it is supported by NSF project and Guangzhou Educational Foundation. And I will be happy to answer your question, and please follow my Twitter. I only use Twitter account for the academic purpose. I do not post my personal things, so it would be not spam. And